about imines, enamines, and Wolff-Kishner, and hydrozones and oxenes. Hydrozones and oxenes should be very, very fast. And then if I have time, I'll also do amide coupling with TCC. Alright, so imines. So what is an imine? An imine is something with a structure that looks like this is an imine, and we're going to get here from a carbonyl. So how does that happen? So the general idea is that carbonyls have a very electrophilic site, and our generic amine here, our generic amine has a lone pair, and nitrogen has a good nucleophile, so what we'll see is they'll have a nucleophilic attack on this carbonyl carbon. There's two formal charges right now, so we can neutralize this charge. We usually do this in the presence of either a base or an acid. In this case, we can do this with another equivalent of our nitro compound. And what that will do for us is you can deprotonate this nitrogen at this. So to make the imine form, we need to essentially remove this oxygen and replace it with a nitrogen. We have a nitrogen in place, we need to remove the oxygen. So what we're going to do is protonate it. So we just used earlier, deprotonate, and we get Alright, so now we need to make this a leaving group. So in order to make a leaving group, we should probably protonate it, because water functions as a pretty good leaving group. So we'll have our acid and protonate our oxygen one more time. Now we have a good leaving group, and a property of nitrogen that's pretty important is that it's a really good pi donor. So what's happening is this is going to form a pi bond, and that's going to kick off this oxygen leaving group, this part of the leaving group. So now we are almost at our final product. This is our aluminium ion. Noted by the double bond and the positive charge on the nitrogen, and then which is the conjugate base from this acid that we had earlier with the deprotonate on nitrogen. And then we are where we want it to be. For enamines, it's a pretty similar concept. You honestly just, instead of having two hydrogens on your amine, you have one. So if I just change this single hydrogen to another R group, so you can still engage in nucleophilic attack, right? The second equivalent can still deprotonate. This is now an R group instead of hydrogen. All the same things. we just deprotonated it. This is an R group now. This is also an R group now. What we'll notice here is that when this kicks down and this leaves, we no longer have an R group here, and we no longer have hydrogen to deprotonate with our conjugate base. Right? So if we can't remove a proton from here, we need to find a way to still stabilize this. And lucky for us, we have an alpha carbon, which is one away from this double bond. And what we can do is use our conjugate base to deprotonate that. And it will kick up, and then we can form our enamine. And our side product will be acids regenerated, so that's good. And then water leaves, so we could either just say water here. In order to drive this forward, I think it's good to use dehydrating conditions, but there you are. Because water's double bond is generally, the double bond between carbon and oxygen is stronger than that of carbon and nitrogen, for reasons unknown. All right. Okay, oximes and hydrogens. So I'm actually not going to draw out this mechanism because it takes a lot of time. It's the same one though. An oxime, something of this form, has a hydroxyl on it, so not too different from just a regular amine nucleophile. You can honestly think of it as quite the same thing. Same with hydrogen. So with these ones you get so this is an oxime and this is a hydrogen. Cool. Why are these important? Well, oximes are just cool. You're going to see their usage later on, I think, the Beckman, because if you protonate this oxygen, it forms like a leaving group, and then you can have like some cool attacks. But for now, we'll just focus on the hydrogen first in Wolff-Kishner. Fun fact, Kishner's PhD advisor was Markovnikov from Markovnikov edition. I think that's pretty cool. Wolff-Kishner is just, the goal is to completely reduce a carbonyl. That is not the one, it's a single one. Just looks weird. And we're going to do this basically, the first step we do is we return this into the hydrogen. So I can drop the entire mechanism. You engage a nucleophilic attack on the first step. We need to essentially get our proton transfer, so we're just going to use this again. Proton transfer. transfers. We have a proton transfer. We use our acidic environment. We protonate this oxygen one more time. Once again, we're forming that good water leaving group. That's our goal right now. Okay, now we have a good lead group. As you remember, nitrogen is a good pi donor. It kicks down and kicks off our water leaving group. Don't forget formal charges. And now we have we just need to deprotonate this again now. So this boy just comes over here, conjugate base, deprotonates, and now we have our hydrogen. So now the idea behind this is that we are trying to essentially, thermodynamically speaking, our best thing to get is an N2, which is this. It's a really good, it's for thermodynamic purposes, so this is going to be what pushes the reaction forward is N2. And what we're going to do to get this is that we will just start deprotonating like crazy. Because these right here, we can think of it as these electrons and these bonds with the nitrogen form two of the bonds in this. We can think of it like that. So we're going to start deprotonating. This requires a new reagents, conditions. We need a base. We need water, which is essentially just a way to give protons, as you'll see later on. Because these protons, when we generate our product, which is like, I'll let them out later. And then we need heat. Okay. So the first step. We have our OH, our base. It's going to deprotonate this nitrogen. What that generates is this nitrogen anion, which at first glance isn't too stable, but that's okay, because we're essentially mostly looking for the end product, and we can draw a pretty crazy resonance form of this because we're looking for the N2. So we'll just do that. These have to move, that means, so we get now we have our water, which is essentially a proton donor. The carbon ion is extremely, extremely basic, so we generate that, we protonate it to fix the charges, and we're going to get now we're going to do a really similar thing to the first step. We're going to get the base again, and we're going to deprotonate one more time. And you can think of this as two steps or one step. Essentially, you're moving the electron density onto that nitrogen again. And essentially it resonates down. and it's gonna break this bond. So now we're gonna have our N2. This is really important. This is what drives the reaction, is this leaving, this right here leaving. And now we're gonna have this like carbon anion, which looks pretty unhappy, but lucky for us. Our protons available. And there we go. These protons right here, you can think of them as being moved around. These two protons are essentially right here. They've been moved. I'll do amide coupling next after this. But yeah, Wolff-Kishner.